So in this class, I am going to compute the Fourier transform of some elementary signals which were not completed in my previous lecture. So in my previous lecture, I have computed the Fourier transform for delta function, constant function, and decaying exponential and signum function. And now I am going to find the Fourier transform of two more functions, that is rectangular pulse and sync pulse. Two pulses I am taking. So these two pulses are very important, and when you take digital communications or when you take any kind of data transfer, if you take digital data, if you take ones and zeros, they are represented by rectangular pulses. But of course, you can represent the zeros and ones by sync pulses also. And there are raised cosine pulses. They are, you call generally as a pulse shaping in communication systems and data transfer. So that happens. So these, in that applications you come across these things. So if you want to do any frequency analysis, it is needed here to verify these two pulses as their suitability to represent a digit 0 or a digit 1. So that is one of the applications, and there are several other applications too. So let us focus on these two pulses and how their frequency spectrum looks like. Here I am considering the rectangular pulse. It is given functionally by this expression. So x of t equal to 1 unity when time is less than t1, both sides of y-axis, that is both sides of 0. T equal to 0 is in the middle, t equal to t1, t equal to minus t1. Between minus t1 and plus t1, I have a pulse. Below minus t1 and above plus t1, I have zeros. So it is a periodic signal. It is an energy signal. So it is a single pulse basically. And I will try to find the Fourier transform for this. So as usual, you have to substitute in the Fourier transform equation, and here already I have substituted 1 for x of t equal to 1 in this range, that is between minus t1 and plus t1. So I have directly written here the limits, t1 here, minus t1 here. Okay, directly I have written, and I have replaced the given signal with 1 here. This is 1. So when I continue with this, I mean this is normal integration process and substitution of the limits, definite integrals. So if you substitute, you will get this one. Okay, I mean basically it is a 2 times sine omega t1 by omega. This is what exactly you are going to get. Okay, so anyway, let us solve this to some extent. So I am integrating e to the power of minus j omega t. After integration, it becomes e to the power of minus j omega t divided by minus j omega constant basically. Okay, so this is limited by this interval between minus t1 and plus t1. Okay, so now after I substitute, I will take them 1 by minus j omega. This term I will take outside, and because it's a constant. Now after I substitute, I will get e to the power of minus j omega t1 minus e to the power of minus minus plus. So this is plus j omega t1. This is what I have. Okay, so this is plus term. Take minus outside, this minus and this minus will get cancelled. This is plus term, here I will get minus. So e to the power of minus j theta minus e to the power of minus j theta divided by 2j. So I have to multiply the denominator and numerator by 2j. I will get 2 here in the numerator, 2 here in the denominator. So by 2j it is absorbed in this sine function. So 2 is there extra here. Here I have multiplied the numerator with 2 and denominator also with 2. So this is the numerator 2, it is here. Here e to the power of plus j theta minus e to the power of minus j theta divided by 2j becomes the sine function, sine omega t1 here. Okay, because theta is omega t1. And what about this omega that is there in this denominator? So this is how you can easily derive. Okay, now coming to this, I will manipulate this expression in this way. What I have done here, psi, pi I have taken. I want to represent with an argument or angle theta. So theta, this is omega t1 is there. So I am multiplying this with by pi and dividing by pi. So this is pi theta, this is theta. I can represent in the sine pi theta. So what about theta here? I want theta also here. So here it is omega. 2 is here as it is. Omega is there in the denominator here. What I will do, I will multiply this omega by t1 by pi and again multiply by pi by t1. So these two will get cancelled anyway. So I am manipulating to create theta term here. So I have pi theta here. Here I have theta and pi. Okay, sine pi theta is there. So this is additional thing 1 by t1. So 1 by t1 means it goes to numerator t1. t1 to t1. This is 2t1. So 2t1 sine pi theta divided by pi theta. That is nothing but sinc function. This is nothing but sinc function. You know this sinc function, sine theta by sine pi theta by theta. So this is only theta. When I say sinc theta, it is sine pi theta by pi theta. Okay. And what is its amplitude? 2t1. This is the amplitude of this sinc function is. This is the maximum amplitude 2t1. If we plot this one, we will get this function. So here, what is this? Sine theta, sine 0 by 0. In the limiting case, you can find in the limiting case at sine 0 by 0, I mean sine theta by theta, as it tends to 0, it becomes 1. So this is basically in the limiting case, you can find that this sinc function equal to 1. This is equal to 1 and 2t into 1, that is 2t. So at the center, it is at omega equal to 0. At omega equal to 0, what this sinc function becomes? Sinc function becomes sine 0 divided by 0 as limit, I mean basically it is 0 theta. So I can say theta here, theta here. So this becomes 1. So that is 1 into 2t1. This is 2t1 maximum value at omega equal to 0. So here what is this one? This is nothing but theta is nothing but omega t1. So omega t1 means when I substitute omega equal to 0, this becomes 0. That is how you got this. So this is at the center. Its maximum value is 2t1. And you can also show that not only 0 at other points, that is when this becomes you can when this becomes omega equal to 0, and actually in terms of theta if I take, so if I take in terms of theta, this is theta equal to 1, theta equal to 2 here, theta equal to 3 here, like that. Okay, so this is what you have. So at all theta equal to 1 to 0, what is theta here? Omega t1 by pi. So if this is omega, I think it is there in the next slide, so I will explain taking the help of the next slide, this one. Okay, so this is nothing but theta for us. So let us move to the next one. See here I have written already. This is the standardizer sync function, it is called, and in this one theta is the variable and theta is 1, 2, 3. They are integers here. At integer values of theta, you have the nulls. That means the function take becomes 0 at that point. These are the roots of the function. And theta 1, 2, 3 means what? Pi theta. So this is pi theta. If I take, this is pi, this is 2 pi, this is 3 pi, so like that. Okay, so at multiples of pi, I should say that at multiples of pi, the sync function becomes null, it becomes 0, and the maximum is at the 1, that is at the center, because it is a standardized one. Now because you are multiplying the standardized one with 2t1, correct? So what is that you have here? And what about these nulls? These nulls will become, so let us take this omega t1, the argument of the sync function, omega t1 by pi. Let us make this equal to 1. Then what is omega? Omega equal to pi by t1. This is pi by t1. Similarly, at the argument theta equal to 2, omega t1 divided by pi. This is equal to 2. Let us say it is equal to 2. Then what happens to omega? Omega equal to 2 pi by t1. Okay. So like this, for every theta value, you can find the omega. So 2 pi by t1, this is basically t1. Okay. Now see here, this is first null, this is second null. Here see, this is first null is occurring at pi by t1, and second null is occurring at 2 pi by t1. That is in terms of omega, 2 pi by t1. Okay. So this is this is basically the standardizer sync function, and when we convert this into our notation, whatever we got for our problem, so it happens at the first null happens at pi by t1. First null happens at pi by t1. Same thing on the minus pi by t1 this side. Second null happens at 2 pi by t1. Third null 3 pi by t1. So it has infinite extremas. That means infinite maxima it has and infinite minima it has. Okay. And I mean, because it goes up to infinite. Of course, the energy contained in the tails is very, very small. You can almost ignore that basically. Okay. So that is a different problem anyway. So this is what you have. So I should say that in this sync function, most of the energy is contained in the between the first nulls. Most of the energy here. I mean, because if you square this one, this positive negative will become positive. This negative also will become positive. So I will get this kind of all positive humps I have. Okay. So this is called main lobe. These are called side lobes. So it finds in so many applications. You have the if you want to design the antenna pattern, these kind of things are used. When you want to prove the sampling theorem, this function is used. If you want to transmit ones and zeros, you can shape the ones and zeros pulses in this way. So there are so many applications. Both this shape here you are seeing in the frequency domain, correct? So what is the shape of this in the time domain? It is a rectangular pulse. So a rectangular pulse has a Fourier transform of sync function. Okay. So by using the duality, what you will get, if I take sync pulse, if I take the time function as a sync shape, then my spectrum should be like a pulse shape. Pulse, you should not call it as a pulse. It is a rectangular function, you should say. Rectangular box you should say in the frequency domain. Okay, you cannot say pulse. Pulse is applicable only for the time domain. So let us move to move further. So this is what is the Fourier transform. of the pulse. Now we are trying to reconstruct the signal, inverse Fourier transform. 1 by 2 pi x of capital X of omega e to the power of plus j omega t d omega. So this is what I am taking. I am substituting here to get back the signal. This is synthesis equation or inverse Fourier transform equation. So I will get exactly the same thing. If you mathematically do it, analytically solve this, you will get back your rectangular function. Okay, and in this case, for example, if I find the original signal minus the reconstructed signal here from the inverse Fourier transform, if I take this one, the error will become 0. That means it becomes 0. So what it means is the limits are minus infinite to plus infinite. So instead of that, for example, let us say I will take only up to 10 humps like this. Up to 10 only I will take. 10 cycles, up to 10 cycles this side and 10 cycles this side. If I take infinite, instead of infinite humps, if I take 10 cycles this side and 10 cycles this side, this is nothing but 10 cycles here. I am just putting it here as a 10 cycles. Okay, just for our understanding purpose. This side, another 10 cycles on the left side. So total 20 cycles if I take, and if I reconstruct the signal, then what happens? This is greater than approximately 0. It is approximately 0. That means, so I should say that it is greater than 0. It cannot be 0. That means you failed to, so this is greater than 0. So you failed to reconstruct the original shape of pulse. Okay, I mean, that means you are limiting the signal in bandwidth here. You know that if you limit the bandwidth of a signal, because the bandwidth of this sync function, I mean bandwidth of this rectangular pulse, when represented in frequency domain, is infinite, because this side infinite cycles are there, this side infinite cycle, not cycles, I should say lobes or humps or maximas. So this is 10, 10, 20 only I am taking. Instead of infinite I am taking 20. Of course, most of the energy, 99% of the energy is contained within this 10. The remaining 1% or 0.1% will be there in the tails. It doesn't matter. Okay, but still mathematically when you speak, the error is not equal to 0, because you are restricting the signal bandwidth. Once you restrict the signal bandwidth, what happens in the frequency domain? If any bandwidth reduced in the frequency domain, it reflects into the expansion of the time signal. So how it expands? Probably, so this will be some ripple may be there, so it's something like this. So it has expanded in time. This is more than 2t1. This is more than 2t1. Original signal width was 2t1. Now it is more than 2t1. So it has happened because you have reduced the bandwidth of this signal. You have eliminated some of the frequencies. So it is there is inverse relation between the time domain and frequency domain representations of a signal or function. So whatever I am calling as a function, it is equivalently, which a signal processing person and electronics engineer, you can comfortably call that as a signal. So when I say rectangular pulse, it is a rectangular pulse signal basically. Okay, when I say sync pulse, it is a sync pulse signal, sync signal. So like that we have to understand. Now this is, I mean, when I take infinite bandwidth, that means minus infinite to plus infinite, all frequencies if I take, then x cap equal to, that means the reconstructed signal is exactly equal to the original signal, hence its error between these two equal to 0. Error energy, because I am squaring the difference here, so it is error energy becomes 0. So but even then, at the points of discontinuity, what happens? So that is what it is, except at the discontinuity it satisfies the Dirichlet conditions. Okay, what happens at the discontinuity when you reduce the terms? So you will see a crossover point here. It is always 0.5. If the maximum is 1, it is always, the crossover point is always at 0.5. So if I use infinite bandwidth, you won't be able to see this 0.5. If you reduce the bandwidth, the pulse expands. At that time, you can clearly see this 0.5 here. Okay, see, instead of, let us say, instead of 10 cycles, let us say this is, I am stopping somewhere here. This is correct. This is one cycle. This is another cycle. So 2 cycles, let us say 3 cycles. So this is one cycle. This is one cycle. This is one cycle. I mean, I should, calling cycle is wrong actually. I'm loosely calling it as a cycle, or I can say three humps like this. Okay, if I still reduce this, so this is instead of 10 here, it is only 3 at the center, 1, and this side 1 and 1. So I can say 3. When I reduce, what happens to this? The signal expands because bandwidth is totally restricted. So probably my signal will look something like this. Something like this. So what is happening here? The 0.5 is maintained. The crossover is always at the 0.5, but the signal duration here to here, it has the signal duration has become very large. This is the signal duration because you have restricted the bandwidth there. So the signal duration, it is maybe very high compared to the original pulse width. The pulse has spread in this one. In fact, this kind of thing will happen in communication systems. If the communication channel has a insufficient bandwidth, then the pulses which are transmitted over the channel, they are expanded in time. So the time it extends to the other digits. So when you have, I mean, this is a practical implementation. I mean, practical example, because you may think that where all these mathematics, where all these things are used, we are necessarily discussing all these things. It is not like that. So when I take a, let us take one pulse, you are transmitting like this, another pulse, negative pulse, another pulse, 2 pulses positives like this. So this is 1, this is 0, this is 1, this is what you are transmitting on the channel. So what happens here is you have actually, I mean, if the bandwidth is not sufficient, then what you will get, this will spread like this, this will spread like this, this will spread like this. So what happens is this is called, these are 1 0 circle symbols. So this is called inter-symbol interference. So you should see a perfect waveform which causes the lesser interference in the other digits. So these other time slots of the other digits. So this carries a lot of information basically, though it is appearing as a single pulse. So that is the reason I have separately dedicated one lecture for this. Okay, so this is what you are going to study in your digital communications everywhere in future. Wherever you come across, you study the similar things. Okay, so that's why I have discussed about the bandwidth of this sync function and bandwidth of the time rectangular pulse. Okay, now let us move to the next example. So it's just a reverse for this. I want to find the inverse Fourier transform of this one. What is this one? It is a box function. It is ideal low pass spectrum. I should say this is ideal low pass spectrum. That means ideal low pass. What it means? Low pass frequencies. Sharply at omega and at minus omega, the spectrum becomes 0. So between minus omega, sorry, not omega, this is W. So between minus W and plus W, I have the frequencies which have equal energy, equal amplitude, or if I square this, it is energy. So equal amplitude all ones, and suddenly above W, all frequencies are disappearing. There is no power here. These are all zeros this side and this side. So this is called, you should not say rectangular pulse. What is this one? It is the ideal low pass spectrum because it is a frequency domain representation, not the pulse. So this is ideal low pass spectrum, and the equation functional relation for this is capital X of omega equal to 1 when omega is less than W, and when omega is greater than W, it is equal to 0. So that is nothing but this pulse. Now let us try to find the time waveform for this, because what I have to do now, I am given the Fourier transform. I have to find the inverse Fourier transform for this. So the equation for inverse Fourier transform is x cap, that is you are reconstructing the signal. So this is nothing but synthesis equation. You have Fourier transform here, you have e to the power of plus j omega t is here. Okay, if in the forward Fourier transform, this e to the power of this term will be e to the power of minus j omega t. In synthesis equation, it becomes e to the power of plus j omega t. Okay, every time I am reminding you this. Now substitute this. I have one here, one between minus w and plus w. So substitute here minus w and plus w, and 2 pi is there in the definition, and this is 1 multiplied by e to the power of j omega t. Okay, now when I continue as it is, as I did earlier, I will get sin wt by pi t. And see, remember that it is not a sync spectrum, it is not a spectrum, it is a time signal, it is a time signal. So sin wt divided by pi t, that is what you will find. Now I want to convert this into a standardized sync function, that is pi theta. This is pi, this is theta, and I also want pi and theta here. So I have to add some terms here, because only pi t is available here. So I have to convert this by adding few terms, by manipulating the equation. I have to get this term. So in the process, I have 1 by w extra here. This w, it goes to the numerator. So that's why, and this pi is there anyway in the denominator, and this pi, okay, I mean, where is that one? This pi is there in the denominator, and let me change the ink color. So this pi is there in the denominator anyway. This w will go to numerator. So I got w by pi here. And sin theta, sin pi theta by pi theta is nothing but sync theta. This is what is theta term. Okay. So it is a time function basically. Now if I plot this one, I have this pulse. It is a pulse. You should not say that it is a sync spectrum. So many times I am repeating. Generally we do mistake. So this is x of t, small x of t, because this is the inverse Fourier transform of the given frequency function. This is frequency function, capital X, small x is the time function. So now when I convert this, I will get the inverse Fourier transform, and it is a pulse. Now what is the width of this pulse? The width or support of this pulse is infinite. The pulse width is infinite here. So, and the first null in the time domain, this is a time domain null, not the frequency domain null. 0 happens at pi by w minus pi by omega. Okay, earlier it was pi by t1 because that was the time. Now this is the pulse, sync pulse. It is called sync pulse. So what this is called dual property basically. So when I took the rectangular pulse in the previous example, I took the rectangular pulse, I got the sync spectrum. Now if I take the sync spectrum, I mean sync shape as the time pulse, I am getting the box function, rectangular box function in the frequency domain. So if I take one shape, I will get this shape, and if I take this shape, I will get back this shape. So this is called duality in time and frequency domains. Okay. I think it should be okay with these two terms, two important functions. And after this, I want to just say in terms of, I want to illustrate the bandwidth expansion and compression in these cases. So what I have done here, I have taken 3 sync pulses. This is x1, this is x1, x1 sync pulse. Pulse width between the first nulls is very small here. Then x2 I have taken slightly expanded between the first nulls, so it is width is a dilated version of this. I have expanded this pulse, and I have further expanded this pulse. So what is happening? This sync function has a box Fourier spectrum. Capital X1, this is capital X1. So because the width is small here, the bandwidth is, this is small, this is inversely proportional, so bandwidth is high. What is the bandwidth of this one here? 2W1. 2W1 is the bandwidth of this ideal function. Sharp edges are there. This is only ideal. So it is not possible to construct any signal because this, so you can also see this. So this is sync pulse whose width is infinite. So you cannot generate an infinite width. So if I don't generate infinite width, I won't get this box function. And if I reduce in this, if I reduce up to 10 cycles, let us say 10 cycles or 10 humps of this, as I did earlier, what happens here? What happens here? This spectrum will spread like this. That means it is no more ideal low pass signal. It is not ideal low pass signal. The spectrum is spreading here like that. Okay, that is the inverse relation. So now what I have done here? I have expanded the pulse here. So by expanding the pulse in time domain, it is inversely proportional to this. Okay, the bandwidth is inversely proportional to the width of this pulse. So the box function width has come down. Now the bandwidth is between, 2W2. This is 2W2. So what I can say in this case, 2W2 is the bandwidth which is less than 2W1, previous one, because pulse has increased in length, its spectrum has reduced. This box with 2W1 has become 2W2 now, which is smaller than this. Okay. Similarly, if I still expand this pulse or dilate this pulse, what I will do? What I will get? I will get further reduced bandwidth here. That is 2 omega. Sorry, not omega. 2W3. Omega is the variable. W3 is the constant. So 2 omega 3 is less than 2 omega 2, previous one, further reduced. So because here the pulse width has increased here. This is the pulse width. So as the pulse width has increased, so I am calling this as PW, pulse width has increased and the bandwidth has reduced here. Okay. So that is what we have in terms of frequency and time relations of these functions. Okay, I think I will stop it here. Thank you so much for your attention.
Like, share and subscribe. Hit the bell icon for more updates.